Thank you for joining this webinar. I'm Tom Parkerton, and I work as an environmental scientist at ExxonMobil. And I'd like to share with you a presentation that I prepared that was part of a larger short course that was given at the annual meeting of the Society of Environmental Toxicology and Chemistry that was held in Orlando, Florida in 2016. And this CTAC course was entitled Oil in the Aquatic Environment, Sources, Fate, Effects, Monitoring, and Response Options. And I just wanted to acknowledge several colleagues that are listed on the bottom of this slide who provided review and input to this presentation. So before I jump into my presentation, I thought it would be useful to provide a bit of background regarding the development and structure of this course. And consistent with the philosophy of CTAC, the development of this course involved a collaborative initiative across different stakeholders. Support for the course was provided through industry by the American Petroleum Institute, and a steering committee for the course was formed consisting of individuals from different sectors. It was really agreed at the beginning to design the course using a module format that focused on key principles. Each course module was developed by a lead instructor with subject matter expertise, and then others provided review and input from other sectors. So this next slide provides an overview of the different modules and lead instructors that comprised our full-day course in Orlando. And I'll quickly just walk you through these modules. The first module was intended to give a brief introduction to crude oil and petroleum substances, and that's going to be the subject of my seminar today. The second module focused on physical, chemical, and biological processes that influence the fate of oil once released to the aquatic environment, including advection, dispersion, evaporation, dissolution, and degradation. The third module focused on analytical methods used to quantify oil, including both laboratory and field methods, as well as forensic techniques that are used to differentiate oil sources. The fourth module discussed principles for conducting oil degradation studies and practical lessons that had been learned from one of the field's experts over several decades. The fifth module provided an overview of the environmental hazard assessment of oils, including both toxicity to aquatic life as well as wildlife. So, for example, birds and marine mammals. The sixth module described fundamentals of oil spill response and available response options, including mechanical recovery, in situ burning, as well as surface and subsurface dispersants. And this module also provided an introduction to shoreline protection, monitoring, and cleanup methods. The last module described how coupled state-of-the-science oil fate and effects models, such as SciMap, can be used to integrate some of the key principles that were described in the previous modules to really help inform response decision-making and contingency planning. So the reason why I felt it was potentially useful to cover this slide, just to give you a little bit of the background context for the introductory presentation that I'm going to now cover. So this next slide provides the objectives and outlines for the first course module. The objective is to simply provide an overview of crude oil and petroleum substances. The topics covered include the nature and composition of crude oil nomenclature and available crude oil databases. I'm also going to provide a brief introduction to petroleum substance manufacture, as well as associated petroleum substance nomenclature. I'd like to just share some insights regarding current and future global oil supply and demand trends. I'll also briefly highlight some of the types of oil that are released to the aquatic environment, and then conclude with a brief summary of take-home messages and a list of additional resources for further reading. So that's sort of the roadmap for the presentation today. So this next slide covers the origin and composition of crude oil. As you may know, crude oil is derived from the breakdown of kerogen over geological timescales. The kerogen source material is derived from the anaerobic decay of organic matter, often largely derived by marine plankton that had been deposited to marine sediments. The elemental composition of crude oil consists mostly of carbon and hydrogen, with smaller amounts of sulfur, nitrogen, and oxygen, as well as trace amounts of metals. The molecular composition consists of paraffins, which include linear and branched alkanes, naphthalene that are comprised of cycloalkanes containing one or more saturated rings, and aromatic hydrocarbons that are comprised of molecules with one or more aromatic rings. And the last class is asphaltics that include asphaltenes and resins, which are comprised of poorly defined, highly molecular weight and polar compounds. The amount of these classes in crude oils really vary, but a typical crude oil contains equal amounts of paraffins, naphthenes, and aromatics, with the remaining 10% comprised of asphaltics. This next slide summarizes SARA analysis that is routinely used to categorize the different molecular classes comprising crude oil. So let's try to walk you quickly through this slide. One first performs a distillation on the crude oil to remove the most volatile components that boil below 210 degrees C. This then constitutes the light distillant fraction. The residual then is extracted with solvent on the remaining oil to precipitate out the asphaltenes. The fraction that's solubilized by that nonpolar solvent is then separated into saturated, aromatic, and resin fractions. The saturated and aromatics are comprised of hydrocarbons with the example structures that are shown on the bottom of the figure. The resin fraction consists of compounds that are more soluble in polar solvents and often contain nitrogen or oxygen. The asphaltenes, in contrast, are a complex mixture of high molecular weight compounds that are insoluble in both polar and nonpolar solvents. These non-hydrocarbon components determine the observed color of crude oil. And you can see that the triangle plot in the upper right hand of this slide shows how the results of SARA analysis have been used to characterize the compositional range of the world's crude oils. So a common approach that's often used to classify crude oil involves API gravity. And so API gravity is defined by the equation provided on this slide, and it's inversely related to the specific gravity of the oil. The specific gravity is in turn defined as the density of the oil relative to pure water at 60 degrees Fahrenheit. The API gravity is used to classify oils into sort of different general categories: light, medium, heavy, and extra heavy oil. As API gravity decreases, the density increases, and vice versa, as shown on this table. Another naming convention that is often applied to crude oils that dates back to the early days when the quality of oil was readily assessed using one's taste buds are the terms sweet and sour that reflect the objectionable sour taste that's imparted by sulfur that's present in the oil. So sweet crude oils have sulfur content of less than about 0.5%, while sour crudes contain higher amounts of sulfur. Lighter oils generally contain the most hydrocarbons and thus are preferable to refine into products, and from a commodity perspective, typically exhibit a price premium. Heavier oils are enriched with asphaltic, sulfur, and trace metal impurities that are more difficult to extract, refine, and transport, and thus often come with a price discount. Extra heavy oils are highly viscous and are thus difficult to pump, particularly at cold temperatures. Thus, lighter oils may be added to these heavy oils to facilitate transport. So a good example is diluted bitumen, or dilbit for short, that is extracted from the tar sands in Alberta, Canada. Most oils have API gravities that are greater than 10, which is the API gravity corresponding to that of water, which means that they are less dense than water and then therefore will float if they're spilled to a water body. The exception is, though, extra heavy oils that may exhibit API gravities below 10 and hence may sink when spilled into water. The figure in the next slide shows the relationship between the sulfur content of the crude oil on the y-axis and the API gravity on the x-axis from crude oils that have been sampled from across the globe. The different colored symbols denote different geographic regions where the oils were collected, and you can see the general inverse relationship between the sulfur content and the API gravity. So as the sulfur content goes up, the API gravity goes down. Hence, the light sweet oils that plot on the right side of this figure represent the higher quality, most preferred oils. You can see on the top figure on this next slide that the amount of oil recently being produced in the continental U.S. as plotted on the y-axis in units of millions of barrels per day falls into API gravity bins that really reflect the higher quality lighter oils. However, there are regional differences, as shown in the figures on the bottom, that in which we've got plotted oil production in different states as a function of the API gravity. These differences in crude oil quality fundamentally reflect the geological formations that are present in these different regions. So, for example, in Texas, a very light oil is currently being produced, while much heavier oil is being generated from the reservoirs in California. I included this slide just to point out and make you aware that there are databases that are publicly available for obtaining compositional information for different crude oils. And so two examples include databases provided by Environment Canada as well as by my company, ExxonMobil, which can be readily found using a quick internet search. Okay, I'd like to now shift gears and transition the discussion to petroleum substances that are made from crude oil. And this figure, I think, is instructive because it attempts to capture the challenge presented to refiners that need to make petroleum substances from crude oil. You can see that the distillation curve of a typical crude oil, that's denoted by that red curve to the left, represents hydrocarbons that actually are much heavier than the distillation curve that corresponds to the petroleum substance demand that's denoted by the blue curve to the left. The different products that are derived from a barrel of crude oil is illustrated in the picture to the right, which includes well-known products such as gasoline, diesel, jet fuel, fuel oil, and a number of other products such as hydrocarbon solvents, feedstocks for the chemical industry, lubricants, and asphalt. Thus, the refiner's challenge is to use the various chemical engineering processes that are included in a refinery to break or crack and then rearrange the various molecules in crude oil so that the distribution of molecules in the crude oil that's supplied to the refinery matches the required product demand. This next slide provides a summary of some key facts related to petroleum substances. First, these substances are produced from crude oil by refineries. This involves separation via distillation, which is then often followed by a variety of chemical modifications. The petroleum substance contains different hydrocarbon classes with undefined and variable composition, and this is referred to as UVCBs. Some well-known hydrocarbons are largely absent. For example, you think about benzoalpha-pyrene, it's mainly associated with pyrogenic rather than petrogenic sources. However, new structures may be introduced through refinery processes, such as new branched alkanes as well as alkenes that include double bonds in the hydrocarbon chain. Second, the nomenclature of petroleum substances usually reflects the last step in the refining process, hydrocarbon type, and carbon and boiling range. And I've provided an example name for a petroleum substance that you can see in that sub-bullet. So distillates, hydrotreated light, is obtained by treating petroleum with hydrogen. So essentially you're saturating all the aromatic bonds in the presence of a catalyst, and it consists of C9 to C16 hydrocarbons boiling from 120 to 290 degrees, from 150 to 290 degrees C. So that's sort of an example way that petroleum substances are named. Further, petroleum substances are often prepared by blending different refinery streams to meet specifications that relate to performance for the intended use, such as volatility, octane, cetane, or viscosity ratings. And these specifications can change based on season. So, for example, a higher volatility specification on gasoline may be required in the winter than in the summer to ensure that your car starts in cold temperatures. And lastly, petroleum substances are grouped into 12 major categories that are listed here, spanning from very light to heavy distillate fractions. So the types of different petroleum substances generated from a refinery and the associated uses are further illustrated in this next figure. Crude oil comes into the refinery. It's heated to separate the various fractions, which are then further subjected to refinery processes to generate the different substance categories that we just mentioned, from gases containing the simplest of hydrocarbons, such as methane, to the residual tars that comprise asphalts that are used in road construction. So an important generalization is that as the boiling point interval defining the petroleum substance increases, the underlying molecular composition, so essentially the number of structures, increases exponentially, and that's shown on the side of that figure. I also just wanted to touch on the fact that the physical, health, and environmental hazards of various petroleum substance categories have been evaluated systematically by the manufacturers using the globally harmonized system of classification and labeling of chemicals, so essentially the GHS system, which then is used for reporting that information on safety data sheets. And such information can be particularly helpful in the event of a spill. So, for example, knowing if a petroleum substance is classified with the physical hazard of being flammable is a key consideration, for example, for first responders. And my plan is not to go into much detail about the GHS classification scheme, but I do want to simply point out that for the environmental classification of petroleum substance, these classifications are based on aquatic toxicity and ready biodegradation test data that has been generated for substances that fall within these categories. And further details on the hazard classification of petroleum substances can be found at the Kinkawi website, which is the industry association for European refineries. And again, publicly available if you're interested in learning more about GHS classification of petroleum substances. Okay, I thought it might be just of general interest to provide an outlook on oil supply and demand over the next few decades, and these data are taken from ExxonMobil's 2015 Energy Outlook. So let me just quickly try to walk you through this chart. The height of the bars represent oil demand. The colors in the bars represent the various sources of oil supply across the different regions that are listed along the x-axis. And the black horizontal lines represent the corresponding demand in that region. So a few important messages to take away from this chart. First, the Middle East and the Russian Caspian regions remain the dominant exporters, while Europe and Asia Pacific are the primary importers, with really growth demand really being over the next 30 years really being driven by Asia. Also due largely to the growth in natural gas liquids that have been derived from hydraulic fracturing that are shown as orange bars, the U.S. becomes a net oil exporter by 2030. These general import-export trends will be important for dictating the movement of oil between regions over the next foreseeable future. And I just wanted to point out that the ExxonMobil Energy Outlook involves a detailed analysis, and this report is produced every year and is publicly available. So if you're interested in learning more and particularly getting more details and updated information on this topic, I would encourage you to do a quick search on the internet and download the latest version of this report from ExxonMobil's website. I also wanted to just very briefly touch on the different types of sources of oil that may enter the aquatic environment. I think it's important to recognize that there are both natural and man-made oil sources. Anthropogenic sources are depicted by the different pictures and include releases during oil exploration and production, transportation, refining, and supply through distribution, and ultimately consumer end use. And in a study conducted by the National Research Council in 2003, it was concluded that natural seeps contribute almost natural seeps contribute almost 2/3 of the annual amount of oil entering the marine environment, with most of the remainder attributed to consumption of petroleum, with less contributions from extraction and the transport of oil. So this last slide summarizes some of the key take-home messages from this introductory module. First, crude oil is a naturally occurring substance derived from kerogen that is comprised primarily of an undefined and variable composition of different Sarah classes, and those classes include saturates, aromatics, resins, and asphaltenes. Crude oils are classified by API gravity, which is inversely related to oil density, as well as sulfur content. Refineries separate and convert hydrocarbons in crude oil into 12 major petroleum substance categories, and the hydrocarbon complexity of these substances increases with boiling point range that is used to define the different petroleum substances. And global oil supply and demand trends will dictate future regional export and import of crude oil. And both natural and anthropogenic sources contribute to oil in the aquatic environment. And this concludes the information that's covered in this introductory model. I hope that you've gleaned some learnings from this webinar presentation format. And I have included a slide at the end here that summarizes additional resources that may be of general interest for further reading. And I'll leave this slide up for a few minutes before concluding the webinar if you want to jot down some of these references. Thank you for your attention.